In these unprecedented times, why not learn about derivatives? So the point of this video is basically to take the definition of the derivative, which we've already discussed, and reconstitute some familiar rules about computing derivatives. For example, if two functions are both differentiable, then so is their sum, and the derivative of the sum, f plus g prime, is just the sum of the derivatives, f prime plus g prime. We're just going to hack right into the definition of the derivative of f plus g. So we're going to compute this difference quotient, the limit as x approaches a, of f plus g of x minus f plus g of a over x minus a. But what does f plus g of x mean? It's f of x plus g of x. And what does f plus g of a mean? It's f of a plus g of a. When you distribute that minus sign and group terms and split this up into two fractions, you can get right here. But both of those limits were assumed to exist individually because f and g were assumed to be differentiable. Therefore, I can split up the limit of the sum as the sum of the limits and get right there. So because derivatives are defined in terms of limits and we have corresponding rules about limits, this really wasn't that big of a deal to prove. How about the product rule? Well, unfortunately, it's not just going to be an issue of the product of the limit is the limit of the products, and we'll see why. However, here it is, f times g prime, if f and g are both differentiable, does have a derivative, and it's f prime of a times g of a plus f of a times g prime of a, the traditional product rule that we know and love. So here's the proof. Okay, it's going to come in a slightly non-standard order. Remember, we did assume f and g are both differentiable at a. So the first thing I'm going to do is start with that right-hand side, f prime of a g of a plus f of a g prime of a. Now f prime of a can be replaced with that difference quotient. G prime of a can be replaced with its difference quotient, and since g is differentiable at a, it must be continuous at a. So instead of g of a, I'm going to replace that with the limit as x approaches a of g of x. Okay. So pointing at the various objects as we go, this was replaced with that because the derivative existed by assumption. This is replaced with that because since g prime of a exists, it must be continuous at a, and therefore this is just g of a. F of a I'm actually going to leave alone. And g prime of a was replaced with its derivative, which we assumed to exist. Now, in those terms, what we've done, since both limits existed, I expressed the limit of the product as the product of the limits. Okay, so what we had in this first term here, to begin with, was the limit of this times the limit of g of x, and I've just combined them into one limit. And similarly, this f of a was just a constant hanging out here. And since this limit existed, it was g prime of a, I can factor constants into the limit. Now working forward, since both of these limits exist and they both have the same denominator x minus a, I can say the limit of this thing plus the limit of that must be the limit of the sum. But now look here, this g of x times f of a is going to cancel this g of x times f of a right here. There they go, they cancel each other out, leaving behind just f of x g of x minus f of a g of a over x minus a, which is exactly that limit f times g prime. It's f times g of x minus f times g of a over x minus a. Notice we never really had a limit of a product being replaced with a product of limits except up here in a really oblique kind of way. So this didn't just immediately fall out from the definition of the derivative and using corresponding limit laws. So it was a little bit different than the sum law. It was a little trickier than the sum law, so be careful about leaning too much on just saying, oh, this looks like something we already know, so of course it's one line. You've always got to be careful about how this stuff goes. Here are a couple of sample problems that would be useful to expand our library of what functions are known to have derivatives. So assuming you were able to get through this and establish the quotient rule, okay, remember we proved linear functions have very easily computable limits, but we also, as a sample problem, had the power rule for non-negative whole numbers. For natural number powers, we have a power rule. We can also do things like apply the product rule and the sum rule and the quotient rule. So what can you do with powers of x, which are non-negative integers, constant multipliers, adding, taking products, and dividing? you can construct rational functions. So what you've managed to show by now is that rational functions have derivatives wherever they exist, and there you have it. Okay, so we can now compute derivatives of rational functions at will using just our traditional power rule and quotient rule. What about the chain rule? Yes, I agree. I think the chain rule is the most interesting of the differentiation laws. If you compose two functions together, then f of g prime at a is actually f prime of g of a times g prime of a. What you have to assume is that g prime of a exists, so g is differentiable at a, and f prime of g of a exists, so f has to be differentiable at g of a. So under those assumptions, this will work out. So we're going to prove this by taking the appropriate limit, but we're going to go through the sequence-based definition of limits of functions. So when we compute the limits of our difference quotients, we're going to be using the sequence version. So let xn be any sequence converging to a. Now it's got to be in the domain of f of g, because I'm taking a limit of f of g of a bunch of stuff. We're also going to assume that xn isn't equal to a. Remember, in our sequence limit version, your sequence is only allowed to equal a finitely many times. Also, the first finitely many terms do not affect the limit, so just ignore any finitely many terms that are equal to a and just go down the list until you get that point. Okay. Since they're in the domain of f of g, however, they must be in the domain of g. In order to plug a point into f of g, the first thing you do is plug it into g. So the xn's are going to be used to compute difference quotients of f of g, therefore they're in the domain of f of g, therefore they're in the domain of g. So since g has a derivative at a, I can compute the limit of the difference quotient, which means for any sequence xn converging to a, this is going to work out. So the limit as n approaches infinity of g of xn minus g of a over xn minus a had better be g prime of a. So now g of xn is converging to g of a. Okay? Because xn is converging to a and g is continuous, therefore g of xn must converge to g of a. But these are now points in the domain of f. How do I know they're in the domain of f? Our xn was drawn from the domain of f composed with g. So you have to be able to plug it into g and then plug the resulting number into f. And we assumed f was differentiable at g of a. Also, if g prime of a isn't 0, then based on an earlier sample problem, once xn is sufficiently close to a, g of xn can't equal g of a. So we reclaim this property that g of xn isn't just converging to g of a, but it's also not equal to it at least past a certain point. But for computing limits, that's good enough. We've introduced a big assumption here that g prime of a has to not equal 0. Now, since we assumed that f had a derivative at g of a, and g of xn is now a sequence of points converging to g of a, the limit overall exists, therefore it exists for any sequence converging to g of a, and therefore this limit must be f prime of g of a. And since this limit and the one on the previous slide both exist, we can multiply them together. So starting from the left, we have the difference quotient for f composed with g. But what does that difference quotient evaluate to? Well, it just evaluates to this here. Okay. But note that inside the limit, this numerator can cancel that one, and I reclaim exactly this difference quotient. And since this limit exists, it's f prime of g of a, and on the previous slide, this limit exists, it's g prime of a. Since both of those exist, I can expand that limit out and compute them individually and get right here. This was, however, all on the assumption that g prime of a is not 0. So that leaves a big glaring question. What if g prime of a is 0? xn, remember, was converging to a in the domain of f of g. If g prime of a wasn't 0, the big thing we used was that g of xn couldn't equal g of a infinitely many times. But if g prime of a is 0, maybe it does. Okay, now if g of xn equals g of a, you can't divide by this difference because it'll be 0 infinitely many times. So there are a couple of possibilities. Maybe all but finitely many of the g of xn's aren't equal to g of a. Maybe all but finitely many of them are equal to g of a, or maybe there's infinitely many that are and infinitely many that aren't. This is a pretty comprehensive list of possibilities. How many terms are equal to g of a and how many aren't? Okay, finitely many for one and infinite for the other, or both infinite. That's what we've got here. Why is it always cases? This is not strictly necessary in here, but I like proof by cases because they help you narrow down things and attack one little bit of the problem at a time, rather than trying to solve it all at once. I know it can be a bit of a task to organize all the cases, but each individual case I think makes more sense. It's a style that I find myself drawn to a lot. So the first of those cases was, what if all but finitely many g of xn's are not equal to g of a? Well, that's really the proof we already did, okay? If g of xn isn't equal to g of a past a certain point, then you can divide by g of xn minus g of a, and you can do that little cancellation trick, and everything works just like it did before. The only difference is, since you'll end up multiplying by g prime of a at a certain step, you'll end up with 0, and that's great. And we handled that already, and nothing changes. Suppose you kind of have the opposite problem. Past a certain point, every single g of xn is g of a. Okay, so only finitely many times is g of xn not equal to g of a. So if I go far enough into the sequence, all I see over and over again when I do g of xn is just g of a, g of a, g of a, which means f of g of xn past a certain point is really just going to be f of g of a over and over again. It's a constant sequence because g of xn is constantly g of a. So the difference quotient f of g of xn minus f of g of a is 0 past a certain point because the numerator is two equal terms being subtracted. So I'm taking the limit of a difference quotient which is constantly 0 at least once I go far enough into the sequence. And what's the limit of a sequence that is 0 past a certain point? The limit will just be 0. So what will you get from straightforward computation of the limit of the difference quotient? 0, which is exactly g prime of a, namely 0, times f prime of g of a, which is whatever, I don't even care, okay, because I'm multiplying it by 0. So the two situations we've handled so far is here's a, and I have xn as a sequence converging to a, and I'm going to plug it into the function g. What I end up with, once I compute g of xn, is a sequence converging to g of a. Okay, so g of xn is converging to g of a, and now I feed it through my function f, and I compute f of g of xn, and then I'm going to do this difference quotient, f of g of a over xn minus a. If past a certain point, my xn's are converging to a, and my g of xn starts just spitting out g of a over and over and over again, then this numerator is just 0. So I'm going to end up computing the limit of 0 over xn minus a. That limit's going to be 0, which is 0 times f of f prime of g of a, because I don't care what that number is. If I multiply it by 0, I get out 0. But 0 was assumed in this case to be g prime of a, and we have reconstituted our product rule in the specific case where g prime of a is 0 and g of xn is equal to g of a past a certain point. So the two situations we've handled are, what if it past a certain point never equals g of a? Then you can do the cancellation that we did on the previous slide. But if past a certain point it always equals g of a, well then you have a very quick computation to get a limit of 0, which is what the product rule would have predicted. In a sense, it's even simpler in this case. It does take a little bit of thought. You can't just say we already proved it, just like we did on the last slide. But the two things independently, this one is a bit easier because you end up with just a difference quotient that's 0 past a certain point. But what happens if both happen infinitely many times? Now, what we're going to do is we're going to make two subsequences, one where the g of xn is equal to g of a and one where it isn't. And they're both proper subsequences because we assumed they both happen infinitely many times. When g of xn is g of a, we know that the resulting limit is 0. When g of xn isn't g of a, we know that the resulting limit is also 0. And since the original sequence of xn is properly split into two things where g of xn is or isn't g of a and both have the same limit, an old result says if you split the natural numbers into two sets and you look at the two subsequences according to those sets of naturals and both have the same limit, then the limit of the sequence exists overall. And that's what we're going to rely on here. When we compute that difference quotient f of g of xn minus f of g of a over xn minus a, on the subsequence where g of xn equals g of a, you get limit 0. on the subsequence where g of xn doesn't equal g of a, you also get 0. So overall, you must get 0. So in the case where both things happen infinitely many times, you just split it up into the two subsequences and then glue them back together in a sense. Overall, whether one of them happens only finitely many times or both of them happen infinitely many times, in all cases, the difference quotient converged to 0 for any xn approaching a. And the proof of the chain rule is complete because then what we have is, for any xn approaching a, f of g of xn minus f of g of a over xn minus a had limit 0, which happens to be equal to g prime of a times f prime of g of a. Okay, remember when g prime of a wasn't 0, we already did a full proof of the chain rule. All of this later work was just addressing what happens when g prime of a happens to equal 0. And having established that this implies all of this is exactly the limit-based version of the definition of a limit of a difference quotient existing, which was the definition of the derivative existing, and we are done. Yeah, it took a while to get through. The case of g prime of a equals 0, honestly, while it is relatively rare in a sense, usually g prime of a is something else, was more of the work. But we are done. So here's a familiar theorem. Suppose f has a maximum value at a certain point. Okay, in other words, f of x is less than or equal to f of x naught everywhere else. Then if the derivative exists, the derivative must be 0. But not anything about tangent lines, right? So we just look at the difference quotient. The numerator is always non-positive. Okay, the denominator can flop back and forth between non-positive and non-negative, but the one-sided derivatives must exist. So on the one hand, the one-sided derivative can't be negative, and on the other, it can't be positive. The only way that both of those can exist and be the same number is to be 0. We've actually already done this before. Okay, and just to refresh, the proof was basically if I'm at a maximum, okay, so ignore this part, haha. So here is my x naught, so that f of x naught is a maximum. Then as I approach from either side, f of x minus f of x naught over x minus x naught, this numerator is never positive because I'm approaching a maximum. Okay, so f of anything else can't be bigger than f of x. But this denominator flips between bigger than 0 and less than 0, depending on what side I'm approaching from. Therefore, the limit also can be less than or equal to 0 on one side and must be bigger than or equal to 0 on the other. And the only way that happens both times is for it to be equal to 0. And again, this is a proof we've already actually done. Okay, so therefore, if you're at a max or correspondingly a min, and the derivative exists, then the derivative must be 0. Suppose you're at a point where the derivative is 0 or doesn't exist. Okay, because remember, this theorem we just proved said if you're at a max and the derivative exists there, okay, then the derivative is 0. Which means you could be at a max or a min where the derivative doesn't exist. Think of the absolute value function, which comes down to a minimum, but has no derivative at that minimum. So any point where the derivative is 0 or simply fails to exist is called a critical point. So here's an example that we're going to work through, okay? We've got a function f of x, x squared minus 6x plus 6, an interval from 2 to 5. The minimum occurs at f of 3 equals minus 3, and the maximum occurs at f of 5 equals 1. So we're going to prove this. But you might recognize as a sort of problem you probably did several years ago when you took Calculus 1. Find the max and min value of a function on an interval. Yeah, okay, this is honestly the only time we're going to do a problem like this. The point here is not to get the answer, it's to speak through the reasoning of how you get the answer, so that now you can go back and redo all your Calc 1 problems and understand why you're doing what you're doing. So our function is continuous on a compact set. It's important here that the interval 2 to 5 includes its endpoints. It's closed and bounded. Since we're continuous on a compact set, we have a maximum and a minimum. In other words, the problem is not impossible. There is a minimum to find and there is a maximum to find. The derivative, however, does not exist at 2 and 5. Why not? I mean, if you look at the function f of x is x squared minus 6x plus 6, you'd think, well, the derivative is easy to compute everywhere. But we've restricted our domain. The domain is only from 2 to 5, which means it has a right derivative at 2 and a left derivative at 5. But the earlier theorems that we did about maxes and mins and such didn't talk about one-sided derivatives. It talked about derivatives. Since our domain is cut off at 2 and 5, the derivative does not exist there, because I can't, for example, take a left derivative at 2, nor can I take a right derivative at 5. So because we have restricted the domain, the derivative now fails to exist at those endpoints. However, when we compute the derivative of x squared minus 6x plus 6, it only has a single 0, and that's at x equals 3, which happens to be inside our domain. Okay, 3 is in between 2 and 5. So what are our critical points? There's a single point where the derivative is 0, x equals 3. Also, there were 2 points where the derivative didn't exist, 2 and 5. And now we know if the maximum, or minimum, happens at a point where the derivative exists, the derivative must be 0. But it could also happen at a point where the derivative doesn't exist at all. So wherever the max and min are, either the derivative is 0 or the derivative doesn't exist. In other words, maxes and mins must happen at critical points. And now we have 3 critical points, the 2 endpoints in x equals 3. So since that's only 3 points, we can just compute the value. f of 2 is -2, f of 3 is -3, and f of 5 is 1. The max and min exist because we have a continuous function on a compact set. The max and min must happen at critical points, and there's only 3. So these 3 points must contain the max and the min. The minimum is therefore the lowest value, and the maximum is the highest, -3 and 1 respectively. So yes, the minimum is at f of 3 equals -3, and the maximum is at f of 5 equals 1. Notice that f of 2 equals -2 is still a critical point, but it's not a max nor a min. Okay? Critical points are not obliged to be maxes or mins, but maxes or mins are obliged to be critical points. Now let's talk about a more abstract theorem, getting back in line with traditionally how we approach this course. Suppose you have a differentiable function that has an inverse. Okay, remember a while back we proved that a continuous function that has an inverse has a continuous inverse. Now we have a differentiable function that has an inverse, has a differentiable inverse, and you can compute the derivative according to this formula here. Right, derivatives of inverses are not inverses of derivatives, okay? So in this formula, on the left, we're computing the derivative of the inverse. On the right, I do not have f prime inverse. We have 1 over f prime, which is the reciprocal of the derivative, not the inverse of the derivative. It is not f prime inverse, it's 1 over f prime. So the proof is actually quite straightforward. Okay, let's start with that right-hand side, 1 over f prime of a. Since f was assumed to be differentiable, I'm replacing f prime of a with that difference quotient. Okay, now instead of calling this 1 over a limit, I'm just going to call it the limit of 1 over the difference quotient, but 1 over the difference quotient reciprocates as we have on the right there. And because we're not dividing by 0, this is all fine. However, I now have f of x minus f of a down in the denominator, so this is legitimate as long as f of x isn't equal to f of a sufficiently close to a. But we assumed f prime of a was not 0, which means, again, from an old sample problem that hopefully we did, since f prime of a isn't 0, if x is close enough to a, then f of x can't equal f of a. And since we're taking the limit as x approaches a, we're really only concerned with x very close to a. So I'm not ever dividing by 0 here, at least once x is close enough to a. So since f is differentiable, it must be continuous. So if x is approaching a, f of x must be approaching f of a. But we also know that f has an inverse, that's one of our givens, and from an earlier result, its inverse must be continuous. So if y is approaching b, f inverse of y must be approaching f inverse of b, because f inverse is continuous. So if we just swap y equals f of x and b equals f of a, we get that they each imply one another. X approaches a doesn't just imply f of x approaches f of a, but the reverse also holds. X is approaching a if and only if f of x is approaching f of a. So because the function has an inverse, any time I have x's approaching a down in the domain, I'm getting corresponding points in the range that must be approaching f of a because it's continuous. Okay, but if I just imagine rotating this picture around, swapping x's and y's, so now my vertical axis is not the range of the function, but it's the domain of the inverse. So now I have a sequence approaching f of a in the domain of the inverse function. Since the inverse function is continuous, that must be generating a sequence converging to f inverse of f of a in the range of the inverse function. In other words, converging to a in the domain of the original. So let's get back to that computation. 1 over f prime of a, we've already reduced down to this quotient here, the limit as x approaches a of x minus a over f of x minus f of a. And remember, we're not dividing by 0. Because f prime of a is non-zero by assumption, once x is sufficiently close to a, f of x is not equal to f of a. But x approaches a if and only if f of x approaches f of a. Therefore, I can replace the limit as x approaches a with the limit as f of x approaches f of a. Now I'm just swapping x as f inverse of y and a as f inverse of b, and y is f of x and b is f of a, using the notation introduced on the previous slide. And now we exactly have the difference quotient to compute the derivative of f inverse at b, which is exactly the derivative of f inverse at f of a, because that was what b was. And now we have our desired formula. The derivative of f inverse at f of a is 1 over f prime of a. And the reciprocation, yeah, it came from the difference quotient, where the difference quotient has the function in the numerator and the domain down in the denominator, but inverses essentially swap what's the range versus the domain, so you end up reciprocating the difference quotient, and that's where that reciprocal comes from, where you end up with 1 over f prime of a. Okay, moving on, more and more topics. If f is differentiable, we can compute its derivative function. But what if that new function also has a derivative? Well, no surprise to people who've taken calculus. You call these higher derivatives. The derivative of the derivative is the second derivative. The derivative of that is the third derivative, and so forth and so forth. Okay, so we introduce the following notation. If you want to talk about higher derivatives, you put that n inside parentheses. Those parentheses are actually quite important. It's not f to the n of x, it's the nth derivative of x, and the way we mathematicians have decided to recognize that is by putting that exponent in parentheses. It's not the best notation, but it is what we do. You can also just use this d by dx notation, which is a lot less ambiguous. Now, if the nth derivative exists at a point, we say the function is n times differentiable. This is not the biggest leap in terminology. If the second derivative exists, it's called twice differentiable. If the eighth derivative exists, it's called 8 times differentiable, and so forth. So why bother introducing this notion of how many times it's differentiable? Well, yeah, as Lambo says, we know some functions might fail to have derivatives at certain points, which raises the possibility that it might have one derivative but not two, and so forth. So our definitions should at least account for this. So here's a theorem that very rarely gets brought up, but I think it's at least worth mentioning, that higher derivatives are an additive process. So on the left side, what we're doing is we are taking the mth derivative here, and then of the mth derivative, compute n derivatives of that. That is equal to first taking the nth derivative and then taking m derivatives of that, which is also equivalent to just taking the original function and taking the n plus mth derivative. In other words, if you're doing a higher derivative, like you want to compute a 7th derivative, you can say, take the 7th derivative of the function. You can say first compute 2 derivatives, then compute 5 more. You can say first compute 4 derivatives, then compute 3 more. They're all going to be equal to one another. And it might seem quite obvious that doing something 7 times is the same thing as doing it twice and then doing it 5 times, but it's still something that I think is worth addressing, even if very briefly. The proof is not very long. So imagine capital D is a differential operator. It's a function that acts on other functions. If you plug in a function, capital D of that function is its derivative. So this is now a function that takes differentiable functions and spits out other functions. And all we're saying here is that if you apply this operator m times and then n times, it's the same thing as applying it n times and then m times, or maybe the other way. I don't even remember what I said. Though the point is, now we've rephrased derivatives in terms of just composition of functions. Namely, we're composing the function capital D with itself. And function composition obeys this property in general. Forget the fact that it's a derivative, it's just a composition of functions. If you compose the same function with itself over and over again, the fact that functional composition is associative gives us this result quite directly. Okay, so higher order derivatives can be computed in any order you want. And yeah, you've probably always just assumed it worked that way. It is a fairly intuitive result, I'll grant you. Okay, here's a sample problem to work through. I like to call it the binomial Leibniz rule. Suppose you have a product, f times g, and you want to take a higher order derivative of it. Okay, so this is why it's a Leibniz rule or a product rule, but I'm plugging this product rule into a higher order derivative. Then you get this expression over here. And remember, those exponents in parentheses mean that's how many derivatives you're doing. So we have this nasty sum of binomial coefficients towards products of higher order derivatives. Why would a higher derivative look like a theorem about sums to powers? The product rule, which this is kind of generalizing to higher order derivatives, the product rule already gives us a sum of two different terms. So it's reasonable to think that if you do this many times, you get a sum of many, many terms. A hint to how to prove this, do it by induction. And for the binomial coefficients, we have this Pascal's rule for how various binomial coefficients can be combined with one another. Again, please pause and work through these problems. They're here for your benefit. Also, we might use this later on, and it's nice to have it proved. All right, so hopefully you worked that out. Once you figure out how the pieces click together, it's rather elegant, but let's move on. I want to close out with something called fractional derivatives. So let's think back to that derivative operator. It has this additive property. Okay, if you apply it n times and then m times, it's the same as doing it in the other order. What if that additive property could be extended to non-integer values? So for example, I might call the alpha derivative of x, where alpha is any kind of positive real number. And I might say, I don't really know how to compute it, but I want to obey this property that if I can define derivatives to arbitrary powers, if I do the beta derivative and follow it by the alpha derivative, I want to get the same thing as if I had done the alpha plus beta derivative. This is just like how we computed higher derivatives before, but I'm actually not requiring these powers or how many times I've taken the derivative. I'm not requiring them to be whole numbers, which means I'm trying to come up with a definition of something like, what happens when I don't take the first derivative or the second derivative, but I take the 1.3 derivative? What would that even mean? Well, whatever it means, I want it to obey this property. We're going to call such things, if they exist, fractional derivatives. Now, fractional derivatives might seem like, a bridge too far. This is just way too abstract and meaningless, because what does it mean to do something half a time? How can I take half a derivative? But as an abstract idea, it might seem kind of interesting. Suppose fractional derivatives exist. Let's just look at the half derivative. All we're saying here is that if I take the half derivative and I follow it up with the half derivative, that should be the same thing as taking one whole derivative. Now, powers of x have very predictable formulas for whole power derivatives. So the derivative of x to the n is just n times x to the n minus 1. So if there's a general formula for powers of x for half derivatives, if I apply it and then I apply it again, I should somehow end up exactly here. So one way that might happen, for example, is suppose that the half derivative of x to the n is something times x to the, now when I take a whole derivative of x, the power goes down by 1. So if I take the half derivative of a power of x, maybe the power goes down by a half. Well, now what happens if I take another half derivative of that? Some constant here times x to the n minus 1/2. Now, hopefully, if this is just a constant, constants factor out of half derivatives just like they do for whole derivatives. Maybe, I mean, we don't know that. We're just kind of spitballing here. So maybe I get out a constant here. Now I'm taking the half derivative of a power of x, and we're crossing our fingers and hoping that the power rule applied to a half derivative is to throw out some constant and then reduce the power by 1/2. Since we already reduced the power by 1/2 the first time we took a derivative, now that I do it again, I take down another half, and notice that now this power is just n minus 1. So I have some constant times x to the n minus 1, which is exactly what we wanted to get. The question is, what should those constants be so that their product is n? Now, we're not really going to delve into this too much or figure out exactly what constants should go there. What really helps is to assume that fractional derivatives are linear operators, that they do distribute across sums like whole derivatives do, and that constants do factor out just like they do for traditional derivatives. If you assume that fractional derivatives are linear like this, then you can start to prove some interesting things about what the half derivative of a power of x needs to be. We're not really going to get into it, okay? But you are encouraged to search out more information if this sort of thing strikes your fancy. Maybe that's you. Maybe it isn't. But fractional derivatives are not useless. They have been used to study things like how water diffuses through the Earth, a porous media where some channels allow water to flow at certain rates, but it's blocked in other ways, something porous for water to go through. The manner in which fluids flow through that has been modeled using fractional derivatives. So these are not totally abstract and stupid. They've actually been put to really good use, which might, assuage your concerns if you're concerned about the application of math. As crazy as this sort of idea of a fractional derivative sounds, they are useful. That is going to be the end of this video. Fractional derivatives, we're not really going to come back to them. But as I said, if you think they're interesting, go ahead and seek out further resources. Otherwise, we're going to come back and keep working with normal traditional whole derivatives in the next video.